Good afternoon, everyone, and welcome to our seminar today, which is titled The CYGNUS Models for the Spectral Energy Distributions of Galaxies and Their Supermassive Black Holes. Our speaker today is Professor Efstathiou, who is currently Vice Rector of Research and External Affairs and Secretary of the CYprus Research and Innovation Foundation and he's currently placed at the European University of Cyprus. His research interests lie in the area of infrared astronomy and cosmology, galaxy formation and evolution, star formation and active galactic nuclei. He has done pioneering research on radiative transfer modeling of the spectral energy distributions of galaxies and has developed models for the emission of almost every type of galaxy over their complete spectrum. His models have also been used for the interpretation of galaxies discovered in a number of extragalactic surveys. He participated in extragalactic surveys with the Infrared Space Observatory, the Spitzer Space Telescope, and the Sublimeter Camera Scuba. He is currently involved in the scientific exploitation of surveys with the Herschel Space Observatory and a survey that searches for highly extinguished supernovae and tidal distribution events in luminous infrared galaxies using adaptive optics on 10-meter class telescopes. He also continues his work on radiative transfer modeling of galaxies. Professor Efstathiou, thanks very much for your presence today and your talk today. Over to you. Thank you very much.
Thank you very much, Stelios, for the very kind introduction and the invitation to give a talk in this series organized by the Cyprus Institute. We are good users of the high performance computing facility of Cyprus Institute for a number of years, but we always hope that we'll do more use. And thank you very much again for the invitation to give this talk. So let me first try to give you some justification for this long title by looking at this, the next slide. Okay. Looking at this slide here. First of all, what do we mean by spectral energy distributions of galaxies? What do we mean by CYGNUS? Why do we pursue this line of research? Traditionally in astronomy, we take pictures of the sky. Originally, people used to take photographs of the sky. Now we take pictures with instruments, we process the information, and we construct images like the one we see on the left, which is an image of a nearby radio galaxy known as Centaurus A. It's one galaxy in the Centaurus constellation. And it's a very interesting local galaxy because it's a galaxy where we believe we have, it's a recent merger of two galaxies probably. We have the symbiosis of star formation and an active galactic nucleus. The event that is related to accretion of matter onto a supermassive black hole. It's a very interesting galaxy. You can see radio jets coming out of this galaxy. It's very interesting. But unfortunately, we don't have the luxury to have images like this for galaxies, for these more distant galaxies. For example, on the right, we see information on a galaxy we recently discovered, which is at redshift 4.3. Redshift 4.3 means we are looking at a galaxy which existed 1.4 billion years after the Big Bang. We are now at 13.7 billion years. For this type of galaxies, which are extremely interesting, if you want to study the first galaxies in the universe, how galaxies evolved in the universe. For this kind of galaxies, we don't have the luxury to have images like this on the left. What we have usually is information on, we can measure the energy emitted by objects like this at different frequencies, at different wavelengths. And this gives us this so-called spectral energy distribution, the distribution of how the energy of this object is distributed through its spectrum. And the interesting thing is that these two approaches, looking at an image and looking at the spectral energy distribution, are complementary, because you can learn a lot by studying the spectral energy distributions of galaxies. You can study, for example, in the local galaxies, and I'll show you some examples in this talk. We have the luxury here for local galaxies to see both at the image and at the spectral energy distribution. And if you like, you can train our approach, our models to interpret this kind of more distant galaxies for which we don't have the resolution, the images, even with the best facilities in the world, even with things like the Hubble Space Telescope, even with the James Webb Space Telescope, which is going to go up later this year. Okay, this galaxy here, I'm going to show this later. It's a galaxy we recently published this result in a paper, and I will say more about this later. The lines you see here are the models we have as part of the CYGNUS project. CYGNUS, as we'll see later as well, it stands for CYprus Models for Galaxies and Their Nuclear Spectra. CYGNUS, of course, is a famous constellation. Doesn't just mean CYGNUS. It's a famous constellation on the sky, and there's a very famous galaxy, actually, Cygnus A, which is very similar to Centaurus A. It's a radio galaxy. Okay, so that's a kind of explanation of what the title of this talk is about. Now, what can we learn by studying the spectral energy distributions of galaxies? We can learn a number of things. For example, we can study the physics of how stars form in galaxies. Okay, and I have a slide for each of these bullet points here, which I'm going to go in more detail. I'm just outlining the things we can do here. We can also study the physics of active galactic nuclei. As I said, active galactic nuclei is the term that is used for the phenomenon where we have accretion of matter onto a supermassive black hole, a black hole which may have a mass billions of times as much as the sun. And this process, this is a generalization of the quasar phenomenon, which I'm sure you must have heard, where you can generate lots of amount of energy in a very small volume. Okay, we can then, by studying the spectral energy distributions, we can study the effect AGN have on star formation, which is a very interesting area. We can study the history of how stars formed in the universe and how accretion onto these supermassive black holes evolved in the universe. And we can also, using information and models for spectral energy distributions of galaxies, we can incorporate these models into simulations of galaxy formation and evolution and make sure that our understanding of how galaxies formed and evolved in the universe is self-consistent. Okay, so this is the slide about the star formation side. This is a very interesting diagram, a very popular diagram in galactic astrophysics, which it's what we have here is a plot of the stellar mass on the horizontal axis, how much mass a galaxy has in stars. And on the vertical axis, at the time we are observing it, of course, because we are observing here galaxies at around redshift 2, okay, about some 10 billion years ago. And on the vertical axis, we have the rate at which stars these galaxies form new stars. Okay, and there is a very popular idea in astrophysics these days that there is a main sequence indicated by the solid line, where we have stars, galaxies which are sitting on this main sequence, and they form stars. They have a good correlation of star formation rate and stellar mass. Their star formation rate is proportional to their stellar mass. Okay, what is interesting though is that there are a number of galaxies, the red galaxies you see here, which are above this main sequence. And what is believed is going on here is that these galaxies, which are indicated here as starburst, which may have a star formation rate 4 or 10 times that on the main sequence, these galaxies are believed to be galaxies where we have interactions between galaxies which trigger more star formation, mergers of galaxies. And this, so for the same stellar mass, you have a lot more star formation. And understanding this diagram is a very important area in astrophysics these days, because it embodies most of the physics about galaxy formation you can think of. Okay, so that's an introduction to this diagram. This diagram is, shows the structure of this so-called the active galactic nucleus phenomenon. You see here at the bottom the supermassive black hole, which may have an accretion disk around it, which generates most of the energy. That's where the energy is being generated. But around this, the supermassive black hole and the accretion disk, we have clouds, which may emit emission lines. We have this thing called the green clouds, something that is called the obscuring torus. I will say more about this later. Okay, this thing here, there is no way you can resolve it. You can see the details of this even with the largest telescopes and for the nearby galaxies. So returning to my main theme here, what we are doing here, we are studying the structure, we are inferring rather, the structure of this region, this very interesting region around the supermassive black hole, by looking at the spectral energy distribution, by modeling the spectral energy distributions. And we learned a lot about this region here by doing this in the last 2 or 3 decades. Okay, here, this is a slide that tries to explain the effect of AGN feedback. Basically, the idea here is that if you have a cosmological simulation that follows the mass in the universe as it evolves during time, you see stars form when gas cools and forms stars. If you allow this process to happen, you would end up with much more massive galaxies than are actually observed. And the way that in the models people can stop this from happening, to agree with the observations, is by introducing the effect of feedback. So something happens which stops the star formation, basically. And on the high mass scale, for the massive galaxies, this is believed to happen from AGN, from accreting supermassive black holes. Supermassive black holes, AGN, once they turn on, they have an effect, an influence on their environment. And this is believed to be the reason which stops star formation. But to actually confirm if this idea is correct, and there are lots of people who doubt that it's the correct model, you need to obviously observe galaxies at different redshifts, at different distances, and see this effect happening basically in their spectra, because basically in astrophysics, we are only observing objects back in time. We have these spectral energy distributions as the only information, basically, and we are trying to interpret the spectra to see what is happening in these galaxies. Okay, so my next slide is another very famous diagram in astrophysics. Is the so-called star formation history diagram, which was introduced 25 years ago, something like that. Where here we see the rate at which the universe has been forming stars as a function of look back time at the top, as we look back in time, or redshift at the bottom. Now, as you can see, there is, okay, there are a number of observational points on this diagram, which, okay, I mean, from redshifts from 0 to 2, there's more or less agreement. You can see a consistent picture. But once you look beyond redshift 2, earlier than 10 billion years, there's a lot of uncertainty. And basically this comes about because we haven't detected enough galaxies at those large distances. We haven't been able to collect sufficient data to understand what they are, to understand their physics. So there's a lot of uncertainty about the rate at which the universe has been forming stars on average over a large volume back in time. And this is a very, understanding this is a very important constraint for models of how galaxies form and evolve. Okay, and again, here the spectral energy distributions are useful in this analysis, because when you observe a galaxy, you want to be able, by studying its spectrum, by modeling it, to understand, to predict, rather, to calculate how much is the star formation rate of this galaxy. Okay. All right, and this is finally the slide which tries to explain this idea that we have cosmological simulations. We see an image on the right. It's not a real image, it's a simulation coming from the Eagle simulation, where you can see that the universe has this filamentary structure. You have clustering. Galaxies are not distributed uniformly in space. We have clusters, we have filaments joining these clusters. We have voids, areas where there are almost no galaxies. Now, how do you compare? This is this simulation only shows you the mass. These simulations trace the mass. There are gravitational engines where you trace how the galaxies cluster together. To compare this picture, the simulation, with observational data, suppose you have an image of a part of the sky like this, you need models to go from the mass to the radiation, to the emission. And that's where these models for how galaxies emit, which we have constrained by studying the spectral energy distributions of galaxies, come in very useful as well. And there are a number of attempts which do this. We hope to do something like this ourselves in our group as well. And I'll tell you more about this later. Okay, now there is a very important point I would like to make here, which comes from it sort of follows from the first slide I showed, that unfortunately in astrophysics, we cannot understand the universe by just observing at only one frequency. So traditionally in astrophysics, we observed in the optical, because you can. This is the first type of astronomy that started. It's you can observe from the ground. You can build large telescopes on the ground, which you can observe in the optical. But there are very good reasons to know that you cannot learn all you need to know about the universe by just observing in the optical. And The reason is the following. There are basically three types of three ways you can generate large amounts of energy in the universe. You can have galaxies like the Milky Way, our own galaxy, which is forming stars at a fairly quiescent rate, let's say, and about 1 solar mass per year for the whole galaxy. One galaxy like the sun, say, every year. We also have galaxies, though, that, as I said earlier, that because they are interacting or whatever, for some reason, they produce much more stars from them, much more new stars as we observe them. And we also have the phenomenon that some of these galaxies, which usually they have a supermassive black hole at their center. All large galaxies usually have a supermassive black hole. This black hole is activated if you have an interaction, and we have generation of energy from this phenomenon, the active galactic nucleus. Now, if this phenomena were just stars or an accreting supermassive black hole, it wouldn't be a problem. You could just observe them in the optical and understand everything we need to know. Unfortunately, things are not as simple as that. In the universe, we don't just have stars and black holes. We have a lot of gas, which is basically this is where the stars and the black holes form from. And this gas in itself is transparent because we can see through the atmosphere, say the sun, okay? But in interstellar gas, there is a small proportion of the mass in solid form, about 1% actually. It's a very small percentage by mass. But because you have these small dust, so-called dust particles, which may be only a fraction of a micrometer in size, this makes the gas much more opaque. You cannot, if you have a lot of these, even a small amount of these gas, these dust particles, they make the gas very opaque. You cannot, if you have a star which is surrounded by a cloud of gas with this tiny amount of dust, you cannot see the star itself because the dust absorbs the radiation. And what it does, then it re-emits the radiation in the infrared from 1 to 1,000 micrometers. So what do we need in order to understand these phenomena, which I tried to sketch here? We need observations of galaxies all the way from the ultraviolet to the sub-millimeter, so-called millimeter, from 0.1 to 1,000 micrometers, about 4 orders of magnitude. And we also need models for how this reprocessing of the radiation, how do you go? Suppose you have stars surrounded by these gas clouds with dust, and you have this phenomenon. The optical UV radiation emitted by the stars is reprocessed to the infrared. You need a model, a calculation, a code that calculates how this happens so that you can compare the observations with the models to understand what is going on. We also need, as I say in the last bullet point here, once you have the observations and the models, you need methods to efficiently compare the two. Unfortunately, the model, these calculations you need to do are very time consuming, very computing intensive. That's why I give this talk to a center which is doing high performance computing here, because you need a lot of computing to, first of all, to calculate the models, and then to the comparison of the models with the observations. Okay. So here, if I just go back here, this is a slide just tries to explain this basic point I tried to make, that this is a plot that shows how the opacity, how the how well the atmosphere absorbs electromagnetic radiation from space. As you can see in the optical, You can see the rainbow colors here. We have good transparency, so we can build large telescopes on the Earth to observe. Similarly, in the radio, there is very good transparency. You can see the radio telescope here. That's why radio astronomy was developed quite early, just after the Second World War. Okay, but there are large parts of the electromagnetic spectrum where the atmosphere absorbs the radiation coming from space, especially, say, you see in gamma rays and X-rays, and the infrared, somewhere between 1 micrometers and 1,000 micrometers. So you need to do observations in these parts of the spectrum from space. I'm not going to talk very much about gamma rays and X-rays, but a lot about infrared. Infrared has to be done mainly from space. There are some possibilities to do stuff from the ground. Okay, but mainly the big advances in this infrared astronomy came from observing from space. And actually, it's actually very hard to do infrared observations from space because you have to cool your telescope as well to a temperature very low to very, very close to absolute zero. You need to carry liquid helium into into orbit with the telescope, and the liquid helium usually lasts for only 2 or 3 years. So the infrared data we have is very we have quite a lot of data now, but we need a lot more. There's not enough space missions have been sent to observe the kind of things you would like to observe. Okay, and I will say more about this later. Okay, here is an example of what we are trying to do here, and just to get another perspective. On the left, we see 4 examples of galaxies where we have data, as you can see, from 0.1 to 1,000 micrometers, from the UV, from the ultraviolet, to 1 millimeter in wavelength. And there's quite a bit of good coverage of the spectral energy distribution. What the lines are the models we have, and this is what we one of the areas where we specialize in our group. We have models, and we are trying to do this so-called spectral energy decomposition. We are trying to understand if a particular galaxy is emitting most of its energy from stars, from an accreting supermassive black hole, or from a quiescent, a normal galaxy. And usually it's a mixture. What we find, it's interesting to do this analysis to find out what is the luminosity in the different components, what is the star formation rate, the stellar mass of the galaxy, what proportion of the luminosity is due to AGN, and so on. Okay. Now, it's a very interesting type of galaxies we are studying, and it's a very important population in the universe for reasons that I've already mentioned. It's the phenomenon that happens when we have the merger of 2 galaxies, 2 spiral galaxies. And you can see this example on the left here is a galaxy known as IRAS 08572, where we see this phenomenon. Now, when we have this phenomenon, first of all, okay, you could see pictures like this. This is from the Hubble Space Telescope, actually. It's a lot of detail. But you could see this phenomenon of the interaction and merger of 2 galaxies before the early 80s. But in the early 80s, in 1983, NASA sent a satellite called the Infrared Astronomical Satellite, who did the first survey of the sky at infrared wavelengths. And this satellite, IRAS, detected about 200 galaxies in the local universe. By local here, I mean the universe which is within redshift 0.2. That's 1 or 2 billion light years in diameter. So IRAS detected about 200 galaxies like this, which were extremely luminous in the infrared, from 1 to 1,000 micrometers. And it was a very new result, a very interesting result. And there was a lot of debate, which to a large extent continues even today. What is the power source of these very luminous infrared galaxies, ultra-luminous infrared galaxies? Is it star formation or an accreting supermassive black hole? And as you can see on the image on the left, it's hard to tell just by, this is an optical image. As I said, it's an HST image, Hubble Space Telescope image. It's hard to tell what it is from just looking at the image. Everybody now understands that you need to study the spectral energy distributions of these galaxies and model them properly to understand what is the main source of energy. And we have a model for this galaxy I'm going to show you a bit later, which gives us an idea what is the source of the energy. Now, I have a video here I would like to show you, which shows this phenomenon of the merger of two spiral galaxies. It's only 1 minute, so please allow me to show this video. You probably cannot hear the sound, but as you can see, we have this very interesting phenomenon where the two galaxies enter into a dance, which may last something between 50 to 100 million years. We are trying to understand the details. And during this interaction, we have these two phenomena, the formation of a lot of new stars and the triggering of one or more supermassive black holes. We may have cases where we have more than one supermassive black hole. And eventually this system becomes probably an elliptical galaxy. So you start from two spiral galaxies, they merge together, you have all this activity for 50 to 100 million years, and then create another type of galaxy. This phenomenon is believed to have been, it's fairly rare in the local universe, but is believed to have been more common in the early phases of the universe. And IRAS detected lots of local galaxies like this, but in the late 1990s, we had another important breakthrough. We had the discovery of similar galaxies like these local galaxies at high redshift. This result was published in a paper in Nature in 1998, which I was privileged to be part of. And the discovery was made in the sub-millimeter. What does it mean? What does this mean? As I said, there's one or two possibilities to do infrared astronomy. Sub-millimeter here, the detection here, the discovery was made at 850 micrometers. There is the possibility, the atmosphere is a little bit transparent at this wavelength, or the 850 millimeters. So you can actually build a telescope on the ground to observe it, to observe at these wavelengths. And this telescope, it's the one you can see on the left, is the James Clerk Maxwell telescope, which is actually located on the top of Mauna Kea, the volcano in Hawaii. And now there is, okay, so this discovery showed that there are large numbers of these galaxies in the sub-millimeter galaxies in the early universe. And a very interesting area of research in modern astrophysics is about trying to understand, to find lots more of these galaxies and understand their physics. Here you can see a diagram which shows that one of the most important, most puzzling results in observational cosmology these days is that there are many more of these luminous mergers at high redshift compared to models. The solid line here is the model the so-called GAL-form model, which is one of the state-of-the-art models for simulating galaxies, simulating the evolution of galaxies. And as you can see, at the redshift mode 3, from 3 to 5, there are many more galaxies observed compared to the model. And this is a very big puzzle at the moment. On the right, we see one such example of a galaxy at high redshift, which we feed it with our models. We are in the process of writing a paper on this. Is fed. It turns out that from the model, it's a combination of star formation and AGN activity. It's a similar galaxy to the ones we see locally. Okay, now I come to the physics, the modeling. The basic problem we are trying to solve here is the radiative transfer problem. As you can understand, we have, as I mentioned, gas clouds with dust. We're talking about radiation here. We have, what we are interested in is to calculate how the radiation is processed, is reprocessed, is redistributed, if you like, from the optical UV to the infrared. This phenomenon, this problem is described by the radiative transfer equation, which is given here. One of the pioneers of the radiative transfer problem was Subramanian Chandrasekhar, who wrote a classic book on radiative transfer, 1960, something like that. And he's actually a Nobel Prize winner, Chandrasekhar. He worked on stellar evolution because this problem is actually fundamental for studying the structure of stars themselves. And that was the main problem, that was the main challenge in astrophysics back in the 50s, 60s. But now this same equation is the equation we need to solve for understanding the kind of astrophysics I'm talking about here today. And of course, this problem is a general problem it's not just in astrophysics. The radiative transfer equation, the radiative transfer problem is a general problem in science. There are lots of other applications. Okay, so but for answering this particular problem we're discussing here, a number of methods have been described. Obviously, the equation we are looking at here is an integral differential equation. That is derivatives, but also an integral. There are two basic methods that have been used to solve this equation. It's the so-called ray tracing method and the Monte Carlo method. In the ray tracing method, basically, you are calculating at a number of positions in the cloud. Let's assume, first of all, that the position is spherical. You have a number of positions in the radial direction where you are interested to find out what is the distribution of radiation coming into this particular position as a function of direction, but also wavelength. Because I remind you that we are looking at wavelengths from the ultraviolet to the submillimeter. And you are interested to find out how the temperature of these particles comes out, because it's the temperature that determines the emission. At the end of the day, you want to look at this cloud from outside and see how it emits from the ultraviolet to the infrared. We don't just have absorption here, we have scattering, which is another very challenging problem. But anyway, there are methods that solve this problem. We also have the Monte Carlo method, as I said. In the Monte Carlo method, you throw millions of photons into into the cloud, and you just follow their interaction with particles. And at the end of the day, you observe from outside what you see. The first spherically symmetric models were developed in the mid-70s. The first axisymmetric two-dimensional models, which are essential, so I'm going to see they were developed in the early 90s. And this is where I mainly worked on the first parts of my research career to develop an axisymmetric radiative transfer model. And now we have fully three-dimensional models, mainly with the Monte Carlo method. Okay. Okay, and now come to CYGNUS. As I said, CYGNUS stands for CYprus models for galaxies and their nuclear spectra. And what it is a collection of radiative transfer models, which we have developed over the last 2 or 3 decades. We have models for AGN tori. I'm going to explain next, probably what do we mean by this. Models for a burst of star formation, kind of the phenomenon where we have lots of stars happening at the same time, and models that model an object like the Milky Way, a spiral normal galaxy. As I say, these models were developed, these models go back to early developments in the mid-90s, but we are still continuing to develop new versions of these models. For example, here you see the starburst model, schematic of the starburst model. What we have here, we have an ensemble. You see what is happening here. Stars don't form out of, they form in dense clouds. So we have here a collection of clouds, spherical clouds, say, in which stars form. Now, the clouds and the system, each of these clouds of evolves, doesn't stay fixed with time. The stars, once they form, they have an influence on their environment. They create winds, there's lots of radiation. So you see these clouds are not the same. They're at different evolutionary stages, we should try to follow in this model. And for each of these clouds, we calculate its spectral energy distribution. We build a model for the whole event. And there's an evolution of there's a prediction on how the spectrum of this starburst evolves with time from 1 to 10 mega years. As you can see, the spectrum is different. And at the end of the day, I remind you, you need to compare with observation. So it's important to have a model for this phenomenon. Okay, here we have the second type of phenomenon we are trying to model. Here we have the AGN phenomenon. And here I would like to say 1 or 2 words about, I sort of mentioned this when I showed the slide on the AGN the core, the phenomenon around the supermassive black hole. You see again Centaurus A. If we zoom in into the center of Centaurus A, we think that around the supermassive black hole, we have this thing which is called an obscuring torus. There is a cloud, if you like, a gas cloud around the supermassive black hole with lots of dust in it. It's obscure, has a lot of, it's very opaque, but it's distributed in a toroidal geometry, in a disk. And this is what I worked on. This is the kind of problem I worked on, as I say, in the early parts of my career. I developed a model for this toroidal structure, how it emits, how it absorbs, and how it emits. This is the model you can see here. We developed back in the mid-90s. And if I can just show you how the spectrum, it's very important to understand that this thing is opaque, it's very opaque, even to its own radiation. So what you see depends very much on the direction with which you view this toroidal structure. And this is the calculation we did. For example, if you look at this, if I just go back here, if you look at this structure from the top, you will see a very different spectrum than if you look at it from edge on, from the at 90 degrees to it. And so if you, there are a number of models now that do this calculation for different geometries, for different distributions of the material. And it's a very important challenge, really, to determine which of these models is more appropriate, is more is closer to the real thing. And the way to do it is to compare with observations. Okay, so now I come to this galaxy. I return to this galaxy, IRAS 08572 plus 3915. The numbers just come about because we are, as I said, IRAS did a survey of the whole sky. So these are just the coordinates basically on the sky. What we see on the right is our attempt back in 2014 to model the spectral energy distribution of this galaxy. The blue field circles are observations, photometry, and the magenta is a spectrum. It's not a model, it's a spectrum from the Spitzer Space Telescope, which covers the wavelength range from 5 to 35 microns. And the lines, the blue line is an AGN torus model, and the red line is a starburst model. So, and what do we, this is a kind of attempt to do what I said earlier, the spectral energy decomposition. We try basically all of the combinations of starburst and AGN torus models to see which is the combination that fits better this galaxy. And what we found is that this object is actually emitting most of its energy from an accreting supermassive black hole, from the blue line. And actually, if you go to do the calculations here, you find out that about 90% of the energy comes out from the supermassive black hole and not from star formation. And this you couldn't possibly conclude just by looking at the image on the left. This is one of the most important points I would like to make in this talk. You need to study these spectral energy distributions and model them properly with as detailed model as you can have in order to find out what is the energy source of these objects, which is fundamental for the kind of astrophysics we want to do here, to understand galaxy formation and evolution. Okay, we have, after this, after 2014, we developed a model for the, we had an early model in 2003 for the host galaxy, because the idea here is that you can have a starburst and an AGN and/or an AGN, but all of this is embedded in a host galaxy, in a pre-existing galaxy. So you need a model for this pre-existing galaxy as well. And we have two models. We have a model for a spheroidal distribution, mainly a spherical distribution of stars, or a disk. For example, here we see our model, which is under development actually for a disk galaxy, for a spiral galaxy like our own. We exaggerate the vertical direction here. This is much thinner than it looks here. But you see, spiral galaxy is mainly a system where you have lots of stars spread throughout the galaxy, but you also have these discrete clouds where you have recent stars. Okay, I don't know how much time I've got, Stelios.
Well, as much time as you want.
Okay.
Go ahead.
Okay. Oh, now I come to the fitting aspect. How do you suppose you have these models? You have an AGN model, a starburst model for a host galaxy. And when you say a model, we don't mean we have one curve only. We have a library. We have, say, you have of the order of 1,000 models for each component. Okay, and suppose in addition you have data for a particular galaxy. What do? We throw all of these four things into a Markov chain Monte Carlo code, which tries to find the best fit. We are exploring two different codes. One code is called SADMC. It was written by Sir Johnson back in 2013. It's a code which is written in both IDL and Python. And we have good results already with SADMC. But we are also exploring using another code called MC, which is only written in Python. And it promises to be much faster, because this is a challenging problem computationally to get the best fit given these combinations of models. Okay, so once you fit a particular galaxy, you can then go on to post-process the posterior probability distribution to get things like the luminosities, the star formation rate, the stellar mass, the things we want, the AGN fraction, how much proportion of the luminosity is due to the AGN or the stars. Here is a very interesting application we did of this code 2 years ago, which led to a contribution in a paper in Science. Here, and sort of this is probably, I mean, Stelios mentioned in the introduction that I'm also looking at tidal disruption events. This is a very interesting event, the tidal disruption events. They are the events that are related to, you see, you have a supermassive black hole in galaxy. Suppose you have stars circling this supermassive black hole, and then one of these stars falls onto the supermassive black hole. Then you have this phenomenon of a tidal disruption event, which generates an explosion, basically, something that may be 10 times more luminous than a supernova, and lasts for a few million years, sorry, a few years. And so we discovered one such event in the galaxy known as ARC-299, which you can see the image on the left. It's a merger, two galaxies as well. And this was one of the early applications of our method, of the CYGNUS method, to fit the spectral energy distribution on the right and understand this phenomenon. Okay, here is another application in a paper that we recently submitted, where we fitted 42 of these local ultraluminous infrared galaxies. These are two examples of these 42 galaxies where, interestingly, we find evidence that we don't have just one AGN. Okay, we have star formation indicated by the red, but we actually find that we have two AGN and dual AGN. One AGN we see in one direction and one in another. And, I think this is an interesting result. Of course, you expect you are going to have a proportion of these mergers at some point to have two AGN, which eventually the black holes are going to merge. Okay. And another very interesting application I'm going to show now is very related, which I'm going to return to this galaxy I showed you at the beginning, is related to the a survey, we participated, a project called the Herschel Extragalactic Legacy Project. This was a project which attempted to put together the data for 170 million galaxies out to redshift 4 to 6 by combining data from ground-based telescopes, Herschel, Spitzer, these are infrared telescopes. And there's already, the catalog is already done. This was an FP7 project in which we participated, now complete. So there is a huge database here of spectral energy distributions of galaxies. And there are a number of possible projects you can do here. You can select samples from this survey to study. And it was obviously revolutionized studies of galaxy formation and evolution. One interesting example of galaxy we found in the HELP survey is this galaxy I showed at the beginning. We discovered basically a hyperluminous. Hyperluminous is 10 times more luminous than ultraluminous. Okay, we don't want to go into the details. We found a very luminous quasar at redshift 4.3. It's actually only the second such object that was discovered to date, above redshift 4. And as you can see on the right, this was a very interesting application of our approach, both in the applying the models and the SED fitting method with the SADMC code. And we concluded for this object that it's a quasar. 90% of the luminosity is coming from the blue component, as you can see here. Okay. Okay, I'm basically coming towards the end of the talk now. I'm just going to say a few words about the facilities that are coming up, which are going to give us even more data. ALMA actually is already here. It's an interferometer in Chile, which is observing in this small window of the atmosphere, as I said earlier, at 850 micrometers. It's actually a collection of about 64 big telescopes like this. And it's giving already very interesting results. I mean, it's a very competitive facility to get time, but there is always interesting results come out. On the right, we see James Webb Space Telescope, which is due to be launched in October this year. James Webb is a successor. It's a much larger telescope than Hubble Space Telescope, and it's going to observe out to 30 micrometers. It's going to give a huge boost to this type of analysis, this type of work, because it's going to give us very precious data over its lifetime, which is expected to be 5 to 10 years. Again, it's an extremely competitive facility to get time, to get observation data, but a lot of this data will become public at some point, or we are writing proposals with our collaborators to get time. So we expect to have some participation in projects with James Webb data. And these are two other facilities. Herschel was the far infrared telescope that operated between 2009 and 2013. This is the telescope that provided the data for the HELP project I talked about earlier. This was an ESA telescope, Herschel, and Euclid is another telescope which is due to be launched in 2022. It's an ESA mission again. It's an optical near-infrared telescope. Euclid is actually something similar to Hubble Space Telescope, but 100 times faster. So it's going to observe 100 times larger area of the sky at with the same level of information and data as the Hubble Space Telescope, which was, of course, launched in the 90s. There are other facilities, for example, Spitzer I mentioned, radio SKA. There's a very big array of radio telescopes, the the square kilometer array. It's a very big radio telescope facility being built in South Africa and Australia, which is going to revolutionize radio astronomy. And there is a very big telescope, facility LSST, which is going to revolutionize again the optical region. Okay, and finally, as a summary and conclusions for future work, I showed you basic ideas behind this work. We have fairly good models on how the different phenomena that occur when we have activity in galaxies, mergers, star formation, aging, and tori. And we can use these models to decompose the spectral energy distribution of galaxies to understand what they are, and how they, phenomena we had in the history of the universe. We are involved already in a number of projects, but we anticipate involvement in others in the near future. What we would also plan to do is incorporate these models for the emission of galaxies into simulations of galaxy formation and evolution, so-called semi-analytic models, and simulations of mergers. And our models are available on our website, or you can contact me if you like. So I will just leave you with our slide with the website of our center, Aristarchos Research Center at European University Cyprus. If you have any ideas for collaboration, or we'll always be happy to discuss, and I will be very happy to answer any questions. Thank you very much for your attention.
Thank you, Professor Stathiou, for your talk. It was very interesting and educational as well for me. If there's any questions for Professor Stathiou, please raise your hands or unmute yourselves and please ask away. Any questions?
Maybe I can have one.
Go ahead.
Okay. Thank you, Stelio. Thank you, Professor Stathiou, for the very nice talk. It was very interesting, and it's a topic that I wasn't familiar with, so very nice. And I would like, if possible, to have some more details about the Monte Carlo simulations you are performing. And in detail, you said that, okay, you are using ray tracing for the light. So I guess the light is emitted by stars that you put inside the galaxy. And when you do the ray tracing, are you doing corrections of on the trajectory of general relativity, or these are linear linear lines? That would be one question.
Okay, first of all, our radiative transfer codes use the ray tracing method. The method I described first. We don't do the Monte Carlo. We use other code. We have results from other codes because people are very wise to make their libraries available on the internet, and we are using results from Monte Carlo simulations to plug into our MCMC code. Regarding the question about we don't take into account the gravitational redshift or anything like that, general relativity, because the size of these clouds is much larger than the cloud, the central supermassive black hole. We're talking about 2 or 3 orders of magnitude larger scales. So it's all Newtonian here. We don't take into account general relativity. I don't think anybody does that. Nobody is doing that. There's probably no reason to do. It's not. I guess if you are sitting at the inner edge of these torus, supermassive black hole of the AGN torus, then it may have some effect, the ray tracing, but nobody, to my knowledge, takes that into account at the moment.
Okay, yeah, because in my mind that would be a very computational demanding process to take into account such correction to the trace. So I was wondering that. And so also then the galaxies, you when you simulate them, you parameterize them with some macroscopic parameters, so like density and I don't know, what are these parameters that you use, or you actually define the galaxy by putting in the star by star? So that would be another kind of question.
Yes, it's very, of course, we have 3 or 4 parameters for each component. For example, for the starburst, one important parameter, you are right, is the density of the clouds. Another important parameter is the age of the event, because as I said, because of once you form the stars, they interact with the gas, and the age of the event, which is a model parameter. Another important parameter for the starburst is the star formation history. Because if the clouds are different, then it makes a difference at what rate you form these clouds in the last 20-30 million years, because that changes the weight, the number. If you have lots of young clouds which emit differently to older clouds, then you need to take into account the history of how the clouds formed. And okay, that's for the starburst. Say for the AGN, again we have 3 or 4 parameters. We have again the density of the torus, which is parameterized by its optical depth. We can have the radial extent. It makes a difference if it's a compact torus or a more extended one. The inclination, as I said, makes a lot of difference. What also makes a difference, because it's a torus, makes a difference if we have a thin torus, the opening angle, so-called opening angle of the torus. It's thin or if it's small or large, that in most of the models makes a difference. And then there are other parameters for the torus. For example, I didn't mention this at all. You have models which are smooth, like our model. There are models which are clumpy. You have clumps, and there are actually models which are a combination of the two, so-called two-phase model. Combination of smooth and clumpy. And then for the host galaxy, again, you have a number of parameters. You have the optical depth, you have the age of the galaxy, which affects the primary or the optical UV spectrum, and so on.
Okay, thank you very much. Very interesting.
Okay,
thank
you.
So these are the parameters you fit. I mean, you change and then
these are some of the parameters, and then these model parameters in themselves may not be interesting, but they're the ones which you need to fit the models, and then you can work the other quantities which are interesting: the star formation rate, stellar mass, the AGN fraction, the luminosities. That come out of the post-processing of the fits.
So from your fit, you get actually much more information than just saying is as much due to this effect or as much due to the other, but you also can get information about all the characteristics of this galaxy.
Yes, you get, you learn these quantities, basically the star formation rate, stellar mass, luminosities, AGN fraction. You can, in principle, we sometimes work out the rate at which we have supernovae in the galaxy. You can, some applications we do that. You can work out a number of interesting quantities after that. One of the things I didn't mention is that the models for the starburst and the host galaxy themselves, they incorporate the so-called spectral energy distribution, the stellar population synthesis models, which have can have lines in them, emission lines from the different, from hydrogen, the other species, from the gas, and you can calculate quantities based on the properties of the gas as well. Yeah, there's a lot of things you can do and compare with observations eventually.
Thanks a lot.
Thank you, Simona, for your talk, for your question. Vangelis, you have a question also?
Yes, thank you very much. The rest was very interesting. So, okay, I'm not in the field, so naturally, let's say I have many questions, but I would like just to, the one is a little bit very general. So as you say, there are many different models. So is there any way to provide, let's say, error estimates or uncertainty quantification of these models in order to compare predictions from different models and also from the experimental data?
Yes, there are certainly a number of models, and one of the things I am interested in is to do this type of analysis, the MCMC fitting with different combinations of models. And we are, in this paper, I showed you some results of where we model 42 galaxies. We feed the same galaxies with 3 different combinations of models. In most cases, we get consistent results. There's no main worry here. In the other paper, I mentioned the hyperluminous obscure quasar. We also feed it the same SED with our models and with a code called CYGNUS. And we will actually show the results in the paper. Again, we get a consistent picture. So there is no, it's very interesting to do this, I agree, but there are details which are interesting. For example, the exact details of what the correct geometry for the torus is, for the AGN torus, whether it's smooth, clumpy, or combination of the two.
Yes, actually, I was thinking along this line also.
There are important details which are very important to address, and but the only way to do it is by doing this kind of doing the calculations first to the fitting and using statistics to infer which is the best model. Yeah.
Yes, so actually, I was thinking exactly on the effect of the geometry, and let's say small difference in the geometry, because also in some of our problems, let's say we have seen that the final outcome might depend a lot on that. So there, for example, ideas from Bayesian statistics might be useful. In order to infer, as you say, this problem.
Yes, but it's comforting that the relative proportion of the luminosity is probably robust. You can infer it robustly. The details of the components is not so robust, I agree. And something that we should aim to improve as more quality data comes in. There will be a lot, we had a lot of good data from Spitzer, but there will be a lot more better quality data from James Webb coming up. We're looking forward to that.
Okay, and just a last comment, which might not be, I don't know if it's really relevant to your cases, but what is the effect of the magnetic field that there is in the galaxy? I mean, when you were referring to simulations, are these the standard, let's say, magneto-hydrodynamic simulations or not? Not
simulations. Yes, there are. The equal, the one I showed, does not include magnetohydrodynamics, but there is another simulation we are looking at. It's called trying to remember, it's a US simulation, which includes magnetohydrodynamics. And it's a very, obviously, it's a very interesting area to these simulations. New versions come out all the time. We haven't actually, I mentioned that as a possibility. We don't actually do a lot of stuff at the moment with cosmological simulations. Other people do in this area. For example, I mentioned the equal simulation, the group of Martin Baes in Belgium. They did, they plugged in these models into the equal simulation. So yes, now regarding the torus and the star-forming regions themselves, it's also, there are people who do simulations of these regions, including magnetic fields. It's very interesting that a magnetic field can be constrained by the polarization of the infrared emission. I did some work on this back in the late 90s to 2002. If you have a magnetic field, then these grains, dust grains, which are not necessarily spherical, they can be elongated, they can align with the magnetic field. And this gives you polarized emission. So in principle, you can constrain the magnetic field from modeling the polarization. But unfortunately, there's not much data on polarization. There is, so yeah, again, it's an interesting area where we would expect more results in the future. There's ALMA. ALMA is doing polarized, you can get the emission from polarization. And the large telescopes being built on the ground, the 40-meter telescopes, I think that will do, well, polarizers. Spica actually was a very important mission that was canceled a few months ago, had a very big program to measure the polarization of galaxies in the infrared, but unfortunately it was canceled.
The reason for this, just from curiosity, because of the cost?
Sorry, why?
No, I was just from curiosity, the reason for that the program was canceled?
It was a decision by ESA. Actually, the community wrote a letter complaining about this, about the reasons, because it wasn't a very transparent decision. Well, probably related to cost, feasibility. I don't know. I'm not an observer mainly myself. I was involved in the mission, in the proposal, because I'm interested obviously in the modeling side and so on. Unfortunately, it was cancelled.
Okay, thank you very much.
Thank you, Angela, for your question. Any other questions from anyone else? Any comments? No, I don't see any more questions or comments. So with that, I would like to thank Professor Stathiou again for his talk. Thank you very much for this very interesting topic that you're working on, and we hope that Custody can help your group in any way so that you can carry out your simulations and your research better, faster, work on bigger machines that are available in Cyprus and in Europe as well. With that, I would like to thank everyone for joining. I would like to inform you that we will have a new schedule of our seminar series. We will release it out this week or maybe start of next week. It will cover the period up till June July, sorry. So it's our summer program. You get that in an email. And with that, I would like to thank again Professor Stathil, and hope to see you all in our future seminars.
It was a pleasure. Thank you very much. Nice afternoon, evening to everyone. Thank you.
Thank you very much. Thank you very much.
Bye, everyone.
Bye.
Bye-bye.